First, let me thank the organizer for this kind of invitation. It's my first time in Vienna for, say, scientific reasons, so I'm very happy. Thank you for being here. And so today we speak about unified synthetic curvature bounds for Riemannian and sub-Riemannian geometry. This is a joint work with Andrea Mondino, who is here in the room, and Luca Rizzi from SISA. So we speak mainly about this paper, very long paper. So we try to give you some reason to open it, say, and I will also mention some other references that are listed here. So let me start by a sort of introduction. Certainly, I don't have to convince this community that CDKN spaces are interesting. You know very well, so I will not resume the story for you. It will be even shorter. And let me say that these spaces are interesting because they can give us a unified viewpoint through optimal transport to the Ricci bound from below. And these are interesting because, in particular, we can contain limits. Okay, we have compactness and stability within this class. We need uniform control on the Ricci tensor, and for me, a particular interesting, say, limit which can consider is something which is also related to the previous talk, is a family of Riemannian manifolds which converge to the sub-Riemannian Heisenberg group. So if you consider these three vector fields that are here, x1, x2, x3, and in front of x3 you put some epsilon, then you get a family parameterized by epsilon of Riemannian manifolds in R3 that has this frame as an orthonormal frame. So if you look to the metric Gij, this, when epsilon goes to 0, has an eigenvalue which goes to plus infinity. If you look to the inverse of the metric, so if you think, say, in Hamiltonian terms, the Hamiltonian or the inverse of the metric converges to something which is degenerate at every point. Okay, so at every point you have the inverse of the metric, which is non-negative but not invertible. So the sub-Riemannian geometry, you can think to something where you have the inverse of the metric, but it is not invertible. You start from that. So the crucial point here is that this family of Riemannian manifolds converge to something, so which has a meaning, the sub-Riemannian Heisenberg group, and this limit is a good metric space because of this fact that this third direction, which is which will be killed by putting epsilon equal to 0, you can recover by computing the Lie bracket from the other two vector fields. So in some sense, at the limit, you only have a distribution, or horizontal space, in the sense of Andrea talk, Monte talk. But what is interesting is that the Ricci curvature of this family of Riemannian manifolds is not uniformly bounded. So the Ricci is going to minus infinity in the horizontal directions. Okay, so sequence of curvature is unbounded from below, and the second part of the story is that so it is true that sub-Riemannian manifolds are limit of Riemannian manifold, but the curvature is unbounded. We cannot use the standard, say, CD theory. And actually, but I will not spoiler the talks of Giorgio Stefani and also the related talk in the sub-Finchley case by Matteo Magnabosco, sub-Riemannian actually never satisfied the CD condition. The starting point of this was in 2009 when Nicolas Juillet proved that the sub-Riemannian Heisenberg group does not satisfy any CDKN, any classical CDKN, even if he proved that it satisfies some measure contraction property. So then in 2016, Balog, Christian, and Sipos proved that it is possible to have some interpolation inequality for optimal transport in the sub-Riemannian Heisenberg group. I will say something more precise later. And in 2019, with Luca Rizzi, we extended this result, which in the Heisenberg group was, say, based on the explicit expression of the geodesic, to two more general sub-Riemannian manifolds. So the question is whether it is possible to build a synthetic theory which contains both cases. Okay, since you have some good properties of the transport, but the classical CD is not working. So this question is somehow contained in this Bourbaki seminar by Cédric Villani of 2017, and you can see this is part of the text. Is saying that since Balog, Crystal, and Sipos prove that we can use transport, but with some different coefficient, so the text is in French, as you can see, is, say, hoping for grand unification, to have some notion containing Riemannian Finsler, but also sub-Riemannian geometry. So the attempt I will show here is to do such a unification. So this is the outline. I will do a short Riemannian recap, show some difficulties in the sub-Riemannian setting, then some link with the control theory. I will go maybe a little bit outside of the usual path, and then to explain you the approach, novel approach. So I use novel because yesterday Nicola remembered that novel does not mean better, so a novel. Okay, so let us start with the Riemannian recap. So I will focus in my talk to the distortion coefficient. This is the object we have here is a lim sup of what? So it is beta t x y, say x y out of the cut locus. So essentially you fix a point x, point y, you take a ball, and you shrink to x through geodesic. And you denote the interpolating set at time t by ztx bry. And you compute this ratio here. And you go to the limit when the radius of the ball goes to 0. So of course, in the Euclidean case, by homotopy, this number is independent on the point, is to the power n. And say by classical Riemannian computation, you can compute also the volume, at least asymptotically when t is 0. You know that the Ricci is appearing there. Okay, so you see the t to the power n, the volume, and then you have this expansion. So for small t, you see that it is controlled by the Ricci. And what is interesting is that if you know that the Ricci is bigger or equal than 0, then the bound is uniform in t in the interval 0, 1. So you have a comparison result. This is a way of looking to the comparison theorems. And it is interesting that the same assumption, you all know very well, it also implies a Brun-Minkowski inequality of this type. So if I have a positively curved manifold, I have the Euclidean Brun-Minkowski inequality. This is stronger because you can recover the previous estimate by saying that A is a point and B a ball, and then shrink the ball to 0. Very good. In this case, when you have ZT-AB is the interpolation in the sense of the two sets. Good, so I'm just rewriting here the formula in this way by denoting B bar 0 n t, this interpolated, this coefficient, and the Brun-Minkowski now, since here I had 1 minus t and t, I can write as this number power 1 over n and power 1 over n. Good, so we know that in general these distortion coefficients are difficult to compute explicitly, but if you have bound on a geometry, you have bound on the coefficient. So the idea is that if the Ricci is bigger or equal than k on a Riemannian manifold, then you can compare the beta with the model beta, okay? What I want to point out here are two things. The first one is that in the right-hand side, the model beta depends on a parameter which is the distance of the 2 points. And the other thing is that, here I wrote the formula of the coefficient for k positive. You can see it is the ratio of two functions of the same function. In the numerator, it is a function of t theta, and the denominator is just the same function when t is equal to 1, right? This will be interesting later when we want to extend, say, the theory to other coefficients. Good, so the CDKN condition, here I cheat a bit, but you know the theory much better than me. So you can think in this way, the CDKN space is a space where you can think to have a sort of Brun-Minkowski condition with distorted coefficient, right? this is not true because you actually define by optimal transport. I don't want to write it here. I will write something later. But so it is interesting that this condition only depends on the possibility of doing interpolation, so having geodesic, and having a measure. So it works also on an abstract metric space. What we can note is that all these coefficients are all asymptotically linear in some sense, even in the curved situation. The asymptotic of this coefficient is in t, because if you look here, you have exactly t to the power n when t goes to 0. When you raise to 1 over n, you get t. Very good. So now you can move to the sub-Riemannian setting. And if you want to understand what happens when you shrink sets to a point in the Heisenberg group, for instance, you need the expression of the geodesics, which are written here. So the Heisenberg group is a group, also Andrea told us in the previous talk. So we can focus to geodesics starting from the origin. These are the 3 coordinates x, y, z. They are parameterized by 2 parameters. One is an angle, the theta, and one is a variable I called a, which a priori is a real number. And so you have curves that projects on circles, as you see here. The radius of the circle is 1 over a, so the bigger a, the smaller the circle. And then you have the third coordinate, which is the area spanned by the horizontal projection. Okay, so if you don't see this geometric interpretation, you have the formula here. And another interesting property of the Heisenberg group is that we have also the dilations. So the structure is compatible with this non-homogeneous dilation, right? And so, for instance, if you dilate by lambda the ball of radius 1, you get the ball of radius lambda. Good. What happens in the Heisenberg group? So you can see that your distortion coefficient, as if you want to bound with t to some power, you get a sharp inequality with t to the power 5, and which is not equal to 4. 4 should be, say, the dimension which comes out from the homogeneity, right? Which is also the Hausdorff dimension, and it is related with what we say called or defined a geodesic dimension of the sub-Riemannian manifold. And thanks to this, you can see, or thanks to some computation related to this, you can see that, for instance, this Brun-Minkowski inequality is not satisfied in the Heisenberg group. So you would guess that this means that, say, the dimension you should put in the CDKN is 5 and with flat coefficient, but this is not true. Any of this is not true, and Balog and collaborators prove that this is the good Brun-Minkowski inequality you have in the Heisenberg group. So actually what you have to do is to put here in the denominator the topological dimension, which is 3, and the 5, which is here, is appearing here in the denominator. So the weights are no more linear, are t to some power. Okay, more in general, this the fact that the CDKN is not satisfied has been generalized, and I'm sure we will have a nice resume by Giorgio tomorrow, probably. Good. So if you think to this inequality here, and for instance, if you kill the set A, so if you say that A is a point, and you think in terms of the measure contraction property in some sense, then you see that if A is a point, you can raise everything to power 3, and you get to this inequality here. And I want to give a small justification to you to understand why this 5 is the correct number here. So take this t to the power 5, write as t to the power 4 times t, and put the t on the other side. And then you can plug the t minus 4 inside the set by using this dilation, right? So you want to understand why the measure of this set is, say, at least proportional to t for small t. So if you do this game in standard Riemannian manifold, when you contract along geodesic and then dilate, since at infinitesimal scale geodesic and dilations coincide, then of course what you will get in the left-hand side is something which is scale like constant, right? And in this case, it is not true, because if you use the formula I've showed before, and which I wrote it here, so what you have to do to understand what is this set here, you have to take a point, say, let me write it here. Take a point, use a geodesic to shrink it to time t, and then apply the dilation, okay? The point you can see here, if you want to reach a point, say this point here, P, with a geodesic of time 1, you can see you are taking this formula and finding the good A and theta such that when you plug t equal 1, you get that point, right? Then what you do zt of this point, which just means plug t here, and then you dilate by a factor 1 over t. What happens if you put 1 over t? So you should dilate 1 over t, 1 over t, 1 over t squared, right? So you have a t here, a t here, and a t squared here. So you see that everything is a function of at only. So it is like you have the point you reach with a prime equal at and t equal 1, right? So you have exactly this set here, okay? This sort of butterfly, in some sense, okay? So here it is written in terms of S and not of T, but this case is linearly, okay? This is a linear, the volume is linear. So that's the reason of this T to the power 5, in some sense. One possibility of thinking to that. Very good. So what we could prove with Luca Rizzi is that this sort of bound for the distortion coefficient somehow integrates, let me say, to measure contraction property written in this sense. So you can not only having this at a macro-local scale when the radius of the ball goes to 0, but also for the measure of the contraction of sets to point, and also you can go to modified Brun-Minkowski. I call it modified because, say, what you can get from this inequality here is exactly this type of Brun-Minkowski inequality. Okay, you cannot get the one which is associated to the classical CDKN or CD0N. Okay, so using this theorem from the result of Jouet, you immediately can get the Balog one, say. What is behind this equivalence? Behind this equivalence is the fact that ideal sub-Riemannian manifold, so I will not focus here on this definition, but say is a sort of generic case. For instance, if you think to sub-Riemannian structure on contact manifold, they are all ideal. The feature you have behind is the fact that for these sub-Riemannian manifolds, you have interpolation inequalities for optimal transport. Okay, so if you look to interpolation inequalities for optimal transport, you have exactly the same formula you get for Riemannian for the Riemannian case. Exactly the same, where you have to take care and use the distortion coefficient I showed you before. So essentially, say the reason why at this third level you cannot prove the Brun-Minkowski inequality with capital N in the denominator and inner weight is related with the fact that the determinant of the Jacobian does not satisfy a second order differential equation, okay, like in the Riemannian case. Very good. What happens if you compute the Heisenberg distortion? So You take the formula you have here on the blackboard, you do some computation, and you compute the determinant of the Jacobian of the exponential map. What you get? You get that the beta t of Heisenberg, this distortion coefficient, can be written in this term, a sort of, say, model function, beta bar, which is written here, evaluated in what I call A of xy. What is A of xy? Is exactly the good value of A you should put in this formula to reach from the origin the points you wish. Okay. Good. You have a geometric interpretation as a vertical part of the covector defining the geodesic. What is important here is that this is not a Riemannian model function because it is written this way, but here you don't have the function I showed before. And the argument you should plug replacing theta is not the distance of the 2 points, but is this number here. Okay. So if you want to write a CD condition, you have to take into account these two things. Okay, then I want to make a little detour to show a link with the control theory. So you have to keep in mind this expression here, which, by the way, if you see when theta is going to 0, it goes like theta to the power 5, right? You have 1 theta here, 1 theta for the sinus, and this as order 3. Okay, so if you wish, you can think to produce similar distortion coefficient, not only for geometrical situation, but also for this kind of variational problem. These are very simple variational problems where you have a dynamic which is written in this form, x dot equal ax plus bu. You should think as a control, and you minimize a quadratic function, which is u squared minus a potential. Okay. So you have a dynamic, and you're minimizing a cost, and you have a sort of bracket generating assumption, which is written here, called Kalman condition in this language. But the idea is that you can find optimal solutions for this problem. This comes from an Hamiltonian system, and if you wish, you can produce a distortion coefficient. Okay. This might seem a bit unrelated, but I try to convince you that there is some link. So you have to choose A, B, and Q, and then produce this. What you do, you compute your, say, interpolating set by using trajectories from this system now. Nice. What happens is that this number does not depend on the point x, y. And actually, you can compute explicitly is the determinant of matrix n of t over determinant of n of 1, where n coupled with m is a solution of a sort of Hamiltonian system, okay? Like this one, where you have A, B, and Q appearing. Okay, why this is interesting to us? Because if you take the simplest situation, the harmonic oscillator in Rn, where you have x dot equal to u. So if you think that u is your control, x dot is free, right? And you minimize, say, kinetic energy minus a potential. Then what happens is that in the previous language, the matrix A is 0, B is 1, and the Q is capital K times the identity, okay? So in some sense, you can think to this as a Riemannian situation, because I have control on all directions of the velocity, okay? And, okay, this matrix, so B is 1, this means there is no drift, and the potential here is isotropic. It happens that if you plug here A equal to 0 and B equal to 1, you get the Jacobi field equation, the Riemannian one, so you will not be surprised that this formula recover the Riemannian coefficient, right? Depending on K, of course. What happens it happens that you can produce a sort of problem of the same type, where you have, in some sense, two directions that are controlled, like in the Heisenberg group, you have two vector fields you can control, and one that is controlled through the first one, and you minimize this potential, okay? Now I am not explaining the details, how to choose these matrices, but actually you can produce a sort of algorithm, and this system here is a sort of linearized system along the dynamics. It is related to Jacobi fields, right? Like in the previous slides. So if you compute this quantity here for these matrices, you will get exactly this formula, which is the distortion coefficient for the Heisenberg group. So in some sense, this is to say that that coefficient does not pop out from nothing, is related to this class of control problems, and those are related to linearization of, say, the geodesic flow along trajectories. Okay, take this sentence with you. It is interesting to also notice that there is a sort of splitting here, because we have a real, say, a real line here, which gives theta, and the red part which gives you this, okay? So it is a sort of taking out the direction of the motion, right? Like what you do in the Riemannian case. Good. To close this part, I will just comment on the fact that on sub-Riemannian manifold, on general sub-Riemannian manifold, you can produce a comparison for the distortion coefficient in terms of this class of beta. This is also motivation for, say, the abstract part will come later. So if you take 2 points and you take the minimizer joining 2 points, you can, by a sort of algorithm, associate the two matrices A, B, which are given by the bracket structure, a sort of curvature along this curve, and if you have a bound on the curvature, here it is a matrix inequality here, then you can produce a bound on the distortion coefficient. Okay, so the assumption is a matrix comparison. You can produce a scalar comparison, like for the Ricci, but you need more scalars in this case. And okay, also it is important to tell you that a priori this is a result which concerns one trajectory, okay, not all pair of points. Good. So I tried to convince you that in the Heisenberg group, and so also in general in sub-Riemannian geometry, we have encountered two problems. The fact that the model beta is not Riemannian, and it does not depend on the distance when you look in the inequality, but on another function of the geometry, which I called A previously. So we generalize the CD condition in two ways. The first one is to allow more general beta of the form S of t theta over S of theta, where S of theta has some nice asymptotic when theta goes to 0. Okay, and we have this capital B as a sort of dimension. We will see. The second thing is that we endow the space with a gauge G. Here? Yeah, thank you. Is a theta power D, thank you. So the background idea is that a CD beta n condition would imply a comparison of the true beta t x y with the model beta evaluated on the gauge. Okay, so we have a different model beta which stay in this class and evaluate on some gauge which is also associated to the space. Good. So what is a natural choice for S? So as I was saying, you can take an S which is produced in this way, but if you want to take some specific class, you can think that S will be a solution of a matrix Riccati equation, which we had before. In this case, also the D, you can compute it. Okay. What about the choice of the gauge? Okay, the gauge can be any measurable function a priori. Of course, the theory will be much more simple when this gauge is continuous. But since the natural gauge function I showed you before is not continuous at the origin, it is better to take a priori G to be only measurable. The reason why it is not continuous is because when you want to reach these points on the vertical line, this G is equal to 2 pi, but at the origin is reasonable to put G equal to 0, right? So when you approach in this way, this G will not be continuous. And of course, if the gauge has nothing to do with the metric space, you will prove less properties. So you have a natural compatibility between the metric and the gauge, which in the paper we called Meek condition. And essentially, it is saying that along the geodesic, the G scales linearly. Okay, G from gamma 0, gamma t is T, G gamma 0, gamma 1. So it has a sort of similar properties to the distance. Right? How much time do I have? 10 minutes. Perfect. Very good. So also in this case, there are natural gauge functions. Okay, you can take abstract gauge, and later I will give you a couple of general results. But in the context, it is natural to fix some class of gauge. So if you take a sub-Riemannian manifold and you think to have a Riemannian extension of your metric, then you can call capital D the probably my notation is not very good because this D should be equal to this. I'm sorry. What is this? Is the Riemannian gradient of the distance. Okay. You should think that the sub-Riemannian distance is related somehow with the horizontal gradient, right? So this capital D is a sort of small d, but bigger. This is why it's named capital D, because it contains the full gradient, right? And we call a natural gauge function any function of these two objects, so the distance and this capital D, which is continuous, and one homogeneous, okay? In the Heisenberg group, our gauge, when you see A as a function of point, it is exactly one homogeneous, and it is expressed in this way. It is, as I was saying, the vertical part of the covector or of the gradient, because this is the full gradient and you're removing the horizontal part, okay? Just to explain in few words. Good. I will not explain this, but this is just to show you that in this specific situation of sub-Riemannian manifold, if you want some assumption on G, the one you prefer, you want G locally bounded, then maybe you can take your manifold to have a step 2. You want G to be Meek, then you have a natural condition, the sub-Riemannian manifold, to have this property on the G. So there is a dictionary, say, which I will not detail here because I did not discuss the left column, okay? But, okay, the assumption on G are assumption you can check by giving reasonable, say, sub-Riemannian assumption on your space, okay? Good. To go to the final part of the talk, maybe some formal definition on the more abstract definitions. So how do we produce this CD condition? So we start by the classical Boltzmann-Shannon entropy. And then we use to formulate our dimensional condition the Herbart-Cuvada-Sturm say dimensional entropy, which is written this way: x of minus Boltzmann-Shannon divided by n, and we formulate the condition in terms of un, right? So here I also set this notation. These are probability measure with bounded support, and these are probability measure with bounded support in the domain of the entropy. Okay, so where this rho is the density of our measure mu with respect to the reference measure, which is the Gothic M. Okay, just a little bit more formal slides on what is our beta. So you fix your S in the class I was saying before. You will see that this capital D will be a role of dimensional upper bound, and there is also another interesting property, because this is the behavior for theta going to 0, but it is also interesting to catch this big theta, which is the first small theta where the function is 0, vanishes. And this we see it will be a sharp upper bound on the gauge function. It is associated to a Bonne-Meyer's theorem. And then you produce your beta. Okay, you have several conditions as in the classical case. Good. So you produce the CD beta condition in this way. You ask this sort of, say, convexity inequality here of un. So you take any mu0 in PBS and mu1 in P star BS. So this is absolutely continuous here. We require, for some technical reason, these two measures to have empty intersection in the two support, and this is related to the fact that this G in general has a singularity on the diagonal. Okay, so and we require this inequality on un mu t, where mu t is the W2 geodesic connecting mu0 mu1 with respect to un of mu0, un of mu1, and within the coefficient here you have your beta, the beta you are fixed in the class, and the gauge function. Okay, so you produce a definition this way, and you also have an analog MCP beta condition, where you somehow kill one of the two terms. Okay, some remarks. This MCP beta does not depend on the value on n, actually, here, because you can see that it disappears. We allow non-absolutely continuous mu0, and in some sense this technically simplifies the implication, or gives the implication CD beta n implies MCP. It is contained in the theory in this way. And you have the converse implication when the space supports interpolation inequality for densities, which is the one I showed at some point during the talk. So that's the role of the two definitions. This definition is compatible with what we often discuss in the literature. For instance, if you want to recover the classical Lotz-Sturm-Villani, then you simply have to take as a beta the Riemannian beta capital K capital N and small n equal to big N. So here the two dimensional parameters are the same, and you fix as a gauge the distance, which is compatible with what we have seen. And we can prove this equivalence for essentially non-branching metric measure spaces. Our measure contraction property also recover the classical measure contraction property when you take the Riemannian coefficient. The CD condition of Balog, crystalline Sipos are recovered by putting as a beta the beta for the Heisenberg group and small n the topological dimension, and with the gauge, the one I showed you before, and it is also compatible with the Millman conditions. with the minimum condition. For instance, the QCD condition with capital Q Kn, you simply have to choose a beta which is 1 over the constant Q with respect to the Riemannian beta, and the other condition of Millman, geometric topological curvature geometric topological dimension, which contains 2 different dimensional parameters. You see the difference actually here, because one parameter is in the beta and the other one is in the dimension. Okay, so still a few minutes. Okay, I will be very quick. So you have a sort of Boyne-Myers theorem in this case. For instance, I will simplify my assumption. So I'm sorry not to give to you the full statement, but you can see them, of course, in the paper. So if you have a metric measure space with the gauge function g, such that g is bigger or equal than the distance, which this is always true if you take as a gauge the capital D I was showing before, then you have a bound on the diameter of your space, your support of the reference measure, with respect to big theta, which is the first zero of your S function. In the Riemannian case, the S function is the denominator here, and actually the first zero is a bound on the diameter, of course, when K is positive. You have some other property, which you can prove with the curvature dimension condition formulated in this way. Actually, for these two, the MCP is sufficient. The first one says that if you have a curvature dimension condition and you have a non-decreasing property on the beta, then you can prove a global doubling. Okay. In the Riemannian case, this assumption means that K is positive. So here you can put this condition. And of course, you can remove this condition and you get some local doubling in some sense. You have a dimension estimate. If you have your curvature dimension beta n, then you have a bound on the outer dimension of your space, or say the support of your measure, with respect to the d, which appear in the asymptotic of S. This is, you can actually prove this also for the so-called geodesic dimension. I did not show, but you can check. And we also have a generalized Bishop-Gromov, which now is in terms of gauge balls. So you have to remember the picture we did before. You fix a ball, say of radius rho, the external ball, and then you have this set I showed you before, where the G is less or equal than R. And you produce, say, a volume function and a spherical function with this object here. So you look where the gauge is more than R within the ball of radius rho, any rho, you can say rho equal to 1, for instance, and the corresponding spherical function. And if you have the compatibility, so here you see the role of the compatibility between the gauge and the distance, and the CD beta n condition, you have the monotone non-increasing property for the corresponding function. So probably my time is over. You have, so this was a picture not by hand, but it's the same. So probably my time is over. You have other compatibility condition. I will skip. Let me just mention also that there are results about stability and compactness in this class, and other application I did not include, as for instance, the possibility of including in the same CD class the full family of metric spaces converging to the Heisenberg group. So actually you can see within the same CD class the full Riemannian approximation converges to the Heisenberg group, and some other natural application like the convergence of the sub-Riemannian space to its tangent cone. Okay, these are two natural ways of going to the limit and staying in the same class. Okay, I think I stop here, and I thank you for your attention.